Today we're starting with the linear approximation again, so we're still using that idea of linearization from the last lesson. We're going to practice it because it's going to lead us nicely into today's new topic, which is actually very close to the same idea. But the first thing I want to talk about here is really, how do we know what this A value is? Because in all the problems that you saw yesterday and the problems on last night's assignment, the A value was always given. And so I want you to actually have a chance to think through, why are they choosing this particular A? Because it actually is very specifically chosen. If it had been a different number, we actually couldn't have done what we did, at least with it being useful. So, in this case, I need to figure out what A value I'm going to use. That is, what am I plugging in for X here that would make it relevant for finding these two numbers as my estimates. Well, really then what that means is I'm saying, first of all, what are both of these numbers close to that's nice and easy to use for this type of a problem? 4, right? Because the square root of 4 is a nice, easy number to work with, and both of those two numbers are close to 4. So that's why 4 is kind of my starting focus. Now, that means I want this to be 4. What does that mean I want the X to be? 1. And so then when I go and do this, I'm wanting to use an A value of 1. In order to start this problem, hopefully you're starting by taking your f of x with the square root and just rewrite that using a fractional exponent. Then you can go ahead and take your derivative and figure out what f prime of x is. Now when we find the derivative of that function, remember that I am technically having to use chain rule here, because inside here it's not just an x, it's an x plus 3. But when I use chain rule and multiply it by the derivative of the inside, what is the derivative of x plus 3? 1. It just ends up being super simple. They aren't all that simple though, so I'm putting it in there to remind you that we still need to check and see what that derivative is. Now, strictly speaking, you don't have to clean this up into this form, but it certainly does help if you write it like this with the square root and all that. It's a little bit more intuitive, but we can do the same thing that we do next from this version up here as well. Because the next thing I need to do is I actually need to plug in my x value. And remember what x value we found earlier? The A equals 1, so I'm going to figure out what is f prime of 1. And it should get 1/4. So we know then that the slope of my tangent line going through this particular point is going to be 1/4. Now use that to go ahead and find the linearization. That is, write the equation of the tangent line. Alright, so if I'm going to find that linearization, that means I'm going back to the old y equals mx plus b, and I'm plugging in y, m, the slope I just found was 1/4, and x, and I know the x value here is 1 in order to figure out what b is. But what is y? This sometimes is the part that throws people off. Well, notice we know what the original function was, and I know what the x value was. I know the x is 1. So basically what I can do is I can just plug the 1 in for x. So I'm going to do the square root of 1 plus 3, square root of 1 plus 3 is square root of 4, which is 2. So then I know the y value is 2. So you get your y by plugging back into the original function. And so then when we go and find out what that b value is, our y-intercept, I found it to be 7/4. You could also write that as 1 3/4 or 1.75 as you prefer. It doesn't really matter. What does matter is that I want to use the correct notation. This is the linearization, so I am writing L of x. Remember, capital L of x is how we write that for our linearization. And so that then will be 1/4 x plus the 7/4, or 1 3/4 or 1.75 as you prefer. And having done that, I'm not done. Kind of wish we were, right? But we're not. Because I did that just so I can now use that equation, because that lets me approximate these values for these two over here. I can now approximate the value of those two square roots.
Isn't that just the tangent line?
Right, now, with this linearization process, the part that is really tricky for most people is, what do I now plug in for x in L of x? And it's always a matter of what gets me this number. Because I want the square root of x plus 3 to become the square root of 3.98 so that I can estimate it. Well, that basically means x plus 3 equals 3.98, right? So, what would x have to equal here? It'd be 0.98. So it's always a matter of, what am I plugging in for that? Because remember, I started with plugging 1 in. It's not like I started by plugging in 0. And so my x values that are close to that 1 that I plugged in earlier, they're going to be close to 1 as well. All right, so that means that for the first estimate, I'm going to do L of 0.98. And that's going to give me my estimate for the square root of 3.98. And so for our first estimate, we should find that the square root of 3.98 is about 1.995. And then as you're doing the second part, you're saying what's going to make the x plus 3 in this case equal 4.05. So that's why we're going to be plugging in an x value of 1.05. And for that estimate, you should be getting about 2.0125. Now, the weird thing about this process, though, for most people at least, is this whole thing up here. It's that these x's that we're plugging in don't necessarily seem particularly intuitive. And so we're going to look at a different method today to get at the same ideas, but that might be slightly more intuitive. It's really the same idea. It's just a different way of approaching it. To get us ready for that, we're actually going to do the same old process for this conveniently simple equation, and then apply the new method to it so I can walk you through that. But we're going to have to build some connections, so we got to do it this way first. And so you'll notice in this problem, the very first thing it asks us is to find the linearization of y equals x squared. Well, the linearization, of course, that's just the fancy name for the equation of the tangent line, right? So the first thing you're doing is just finding the equation of the tangent line. That means we got to start by finding the derivative of our original function. So I'm going to do the derivative, so dy over dx equals, well, that'd just be 2x. Nice and easy, right? I'm writing dy over dx. Of course, if you're writing y prime, same thing, right? Just different ways of saying the same idea. All right, so dy over dx equals 2x. I can then use that to figure out what is the slope. I'm going to call the slope m here at x equals 2. So we know that the slope of our linearization is 4. That means I can then go and start figuring out what is that linear equation going to look like. So it's going to be y equals, do we know what y is here? Yeah. Yes, we do. Because we know this point up here, the x and the y. So we know the y is 4 there, so we're going to 4 equals mx plus b. M is 4, we just found that. X is 2, again from that point, plus b. Solve for b. You should find that b is negative 4. Our slope is negative 4. And so we have a linearization of L of x equals 4x minus 4. All right, and so, again, thinking about what this really means, here's our general x squared graph, and here's our linearization, our tangent line. And so what we're being asked is, if we know that this point right here is at 2, 4, we want to estimate what is the value right here, just a little bit above it. And we're going to estimate that by finding the value that's actually on the tangent line. So if this x value here is at 2, the x value here is actually just at 2.1, which might seem obvious, but remember in the previous problem where it was like x plus 3, we ended up using 1 instead because it had a horizontal shift in the equation. This equation has no shift in it. And so when we go to plug in for x, thankfully for once, we can actually just plug in the 2.1 for the x here. We don't have to turn into 1.1 or 0.1 or anything like that. All right, so that means that we're going to actually do L of 2.1, which means doing 4 times 2.1 minus 4. The nice part about this one is we don't even need a calculator, right? We can just do this in our head, which is kind of nice because it bears out why we do this. The 4 times 2.1, that's going to give us 8.4. And I'm going to take away 4 from that. So my linearization of 2.1 is 4.4. And so remember what this L of x means. Remember also, basically what we could say is that L of x is giving me an approximation for the value of f of x. So L of x equals exactly 4.4, but f of x would equal approximately 4.4. Now, the weird thing is here, though, is we really do have to keep asking that same question of, what do I plug in for x? Am I plugging in the 2.1, the 1.1, and it depends on if there's shifts. It's kind of messy. So we're seeing a new method today that takes that piece out of the whole process. It makes it hopefully a little bit more intuitive as a result. In order to do that, though, I got to bend your brain just a little bit, which I must admit I don't mind doing. All along, up to this point, we've been using this notation of dy over dx. And we've been saying, okay, that's just the same notation as saying f prime of x, or y prime. It means the same thing. Well, it does mean the same thing. It's just that dy over dx actually is not just notation. The fact that it's a fraction is actually because it literally is a fraction, not like notation where it's like f times x. Obviously, that's not the case. This is actually dy divided by dx. dy is a variable, and dx is a variable. And so because of that, I can actually break that apart and just write my equation just as dy equals. So notice, like, to do that, in order to get rid of the dx out of the bottom of the fraction, I could multiply both sides by dx, leaving me with the equation f prime of x times dx is what dy equals. Now, I'm going to explain that visually so we can see what the heck that has to do with anything. But first, I want to give you a chance to go ahead and write that down in your notes. This is called the differential. And so as a way to try to take a look at why we would actually go through this process, when we're just looking at like different names of the same thing, let's get back to what's really happening here. When we talk about dy and dx, these are the actual meanings of these. dy is the distance, the vertical distance between any 2 points on my tangent line. dx is the horizontal distance between any of those 2 points. Notice that the derivative always tells us the slope of the tangent line, right? Well, slope is rise over run. I'm rising dy, and I'm going on a run of dx. dy and dx basically have just been fancy names for the rise and the run. It's just specifically the rise and the run on the tangent line. And so what this function is going to allow us to do is, it's going to allow us to say, if I know how far I'm going over, I can figure out how far I'm going up on that tangent line, the tangent line that we're using as an estimate for my actual values. Now, just to make it clear, what are we estimating? This goes back to the work that we did way earlier this year where we actually had delta x and delta y in the equations. Delta x is how far we go over, and delta y is how far we go up for the original function, the actual f of x. The deltas became d's when we all of a sudden hit the tangent line. And so delta y over delta x gives us that secant slope, and dy over dx gives us that tangent slope. All right, and so we're going to go back and apply that idea now of the differential to this problem that we did earlier. And so make note on your paper there that we're now doing it by finding the differential, so that you'll be able to tell the different methods and what method did what for you. And so we can now go ahead and figure out the differential of y equals x squared at that point, and then use it. So we notice there's two parts to this. The first part is just to find the differential. Remember the differential, that's the equation we just got. The differential is saying dy equals f prime of x times dx. So dy equals, remember we already figured out what f prime of x was, right? Because it's a nice easy one in this case. The derivative of x squared is 2x. So it's going to be 2x times dx. When it asks you, what is the differential? Find the differential. This is what it's talking about. This is the differential equation. So that's the first part. Now, use it to make a prediction about the value of 2.1 squared. All right, so now we can go ahead and start using this equation. We can see how it gets applied. So, for applying it, we have dy equals 2 times x. What is the x value I'm trying to estimate here? Rather, not the one we're trying to estimate. What is our starting x value? 2. That's the actual x value where I know what the value is there. All right, times dx. dx, remember that picture there? dx is that that horizontal distance between my original and my new point that I'm trying to estimate at. So what is dx in this problem? 0.1. Notice that what this has done for us is it's eliminated that whole process of, well, x plus 3 equals 3.98. Now I have to solve it to figure out what x is and then plug that in. It means all I need to do is know where is the tangent line going through, that's the 2, and how far away from that am I, the 0.1. So it takes away a little bit of that weirdness that we encounter with that other method. And so then that lets us actually figure out the differential. dy here equals 2 times 2 is 4 times 0.1 is 0.4. Yay, we found dy. It's 0.4. So what? Do you see what that actually tells us? Because think back, remember when we did this problem before? It said estimate the value of 2.1 squared. We got an answer of 4.4. I see some similarities, but we did not get the same thing. Why is that? Because remember what dy means. dy is that vertical distance between the original y value and my estimate. So that's why it's at 4.4, because it told me that I start at 4 and go up 4.4. The dy is telling me if I go over 0.1, I'm going to go up 0.4. And I can always find the original value by actually doing that 4 plus that 0.4. And I can get that same value that I was looking for if I'm just looking for an estimate. All right, now we're going to practice this idea with just a straight up abstract find the differential kind of problem. So let's see how far you can get on this one on your own first. Now you notice here that this is a two-part problem. The first part says find the differential dy. So it's saying write the differential equation. And so that tells you to go, let's go back to your notes. So dy equals f prime of x times dx. So what's telling us then is the very first thing I need to do in order to write this dy equation is I need to figure out what is f prime of x going to be. So you got to find the derivative of cosine of pi x. So when I go to find that f prime of x, the derivative of cosine is negative sine, so it's going to be negative sine of the pi x. But notice that since it's pi x and not just x, I'm having to use chain rule here. So that's the derivative of the outer, then times the derivative of the inner function. The derivative of pi x is pi. And if you want to write it just a little bit more simply, you might write it as negative pi times sine of pi x. And so we plug that in for the f prime of x in the differential equation. And then that's going to be times dx. And dx just stays dx there. That is the differential. That is the first part done. So when it says find the differential dy, that's what it's asking you to do. It's just basically finding the derivative, except you got the dy and the dx sitting in there on separate sides. And now that we know that, we can go on to the second part, using it to evaluate dy at these values. And so plug in the 1/3 for x, plug in the 0.1 for dx, and figure out what that equals. And so you plug in the values for x and for dx, and then it's just a matter of figuring out what that equals, which, if I clean it up, makes it a little bit easier to see how I can do this, even just without a calculator. Because, of course, we do remember our unit circle work, right, to remember what sine of pi over 3 is. We got a little rusty on that one. All right, so we can kind of bring it back to that idea of the unit circle and visualize. And really, this is what you're going to want to do to remember that unit circle work, is visualize where the angles are. So here we have our main three angles between 0 and either 90 degrees or pi over 2, depending on how you're looking at it. First of all, in radians, what is the measure of the lowest of those? That is the red one, as I've drawn it here. That's pi over 6. Yep. And actually, let's go ahead and fill in all the rest. The middle one would be pi over 4, and the top one would be pi over 3. So that it turns out that blue one, that top one's the one I'm going to be interested in. I need one other piece of information in order to be able to do this properly. Sine. Is that how far we go up and down? Or is sine how far we go over? You got to know that part. If you don't, make note to yourself so you remember that sine is how far we go up and down. Cosine is how far we go over. So then I start filling in for the sine, how far I'm going up. The pi over 6, that's going up the smallest amount possible, so that's the 1/2. The middle one, the pi over 4, that's the one that's root 2 over 2. And the one that we're interested in way up top here, that's the biggest of the three, root 3 over 2. And so that was a long answer to remind us how we can actually then find that value without a calculator. So it's now negative pi times the sine of pi over 3 is root 3 over 2. Times the 1/10. And I made that 0.1 into a 1/10 just because it's going to make this next step a little bit easier, because the last thing I'm going to do is just write that as one nice pretty fraction, if you can call a fraction pretty that has pi and root 3 in it pretty. But you end up getting a negative pi root 3 over 20 for our dy value, and that will be your final answer for dy. Now, we went ahead and gave that as an exact value there. It's technically about negative 0.27, which I mentioned only just to kind of point out the idea that what this tells us is that if I go over 0.1, my expected value is going down by about 0.27, by that amount.